Hello and welcome to this FMSP online revision recording for the OCR specification, Module M2 Mechanics. And the topic is Uniform Motion in a Circle. Under that heading in the specification we see these 3 points. First of all, understand the concept of angular speed, which we denote with omega, for a particle moving in a circle, and use the relation v equals r omega, which is the connection between linear speed v and angular speed omega, where r is the radius of the circle. Secondly, to understand that the acceleration of a particle moving in a circle with constant speed is towards the centre, and that acceleration is either r omega squared if we're using angular speed, or v squared over r if we're using linear speed. And then thirdly, solve problems which can be modelled by the motion of a particle moving in a horizontal circle with constant speed. So let's look at some key points. First of all, reminders then. Omega is angular speed. It's given in radians per second. So therefore, if you are given revolutions per second, given one complete turn is 2 pi radians, revolutions per second can be turned into 2 pi radians per second. And then v is the linear speed in meters per second. So, converting from one to the other, the linear speed is r omega, or the angular speed is v divided by r. For circular motion to occur, there must be an acceleration towards the centre of the circle. So again, depending on whether we know angular speed or linear speed, there are 2 versions for the acceleration. There won't be any acceleration perpendicular to that, so it's always important to resolve horizontally and vertically when you're doing circular motion. And finally, identify the central force. What force or what components of forces are acting towards the centre of the circle? So F here stands for the resultant force towards the centre, because that will be the force that's producing the acceleration which will give us circular motion. So here are 2 examination questions that I've chosen. And don't forget, you can always pause the recording to read or reread the question if you need to. So this one concerns a particle P of mass 0.4 kilograms, and that's attached to one end of each of 2 light inextensible strings. So P is not able to slide on this string, it's fixed. We've got a length here, 0.5 meters, and given the angle 30 we can work out the radius of the circle. And then, because of the 2 strings, there are a couple of tensions acting. It tells us the string AP makes an angle of 30 degrees with the vertical and is 0.5 meters long. It doesn't tell us the length of string BP, but it does tell us the angle, and this is all shown in the diagram. Here's a crucial piece. The tension in the string AP is twice the tension in the string BP. So if that tension is T, this tension is 2T, and we should need that fact because the first thing we're asked is what is the tension in each string. Then once we've established those tensions, we're asked what is the angular speed of P. Well, I'm going to get as much information as I can on a copy of this diagram. First of all, we've got a mass of 0.4 kilograms. That means there's a weight force down here of 0.4 g newtons. And then of course this dotted line here represents the radius of the circle, and we have the length 0.5 and the angle of 30, so the radius of the circle is 0.5 sine 30 degrees. In fact, given that sine 30 is also 0.5, the radius must be 0.5 times 0.5, which is 0.25 meters. And then, as the particle is performing circular motion, there must be an acceleration towards the center. And given we're talking about omega here, I'll use the version acceleration equals r omega squared. Now we need to think about the forces. So we know that there's a tension here, value T, and one with twice as much tension up here. Now there's a lot of components to draw on this diagram, so I'll see what I can do. I'm going to need to resolve vertically, so I need to know what forces are happening vertically for P. Well, there's a 30-degree angle in here, which we can see from the Z rule, or alternate angles. And of course, the complete angle there, which I won't label in, but that's also 60 degrees, like the 60 degrees here. And trying to get some components of tension drawn on the diagram, well, if I take the 2T tension first, there's a vertical component here, which is 2T cos 30, because it's next to the angle. And then a component in this direction, which will be 2T sine 30 degrees. Because the diagram is getting a bit congested, I'm going to change colour for the next bit. So regarding this force T here, if I split that into components, there's a vertical component here, and that's next to this 60 degrees angle. So that component is 2T cos 60 degrees. And then the horizontal component there is, I'm sorry, that's not 2T, it's a single T cos 60. And this component here is T sine 60 degrees. Okay, well I think I've got as much information on the diagram as I need. And basically, there's not a lot I can do. I can resolve in two directions, and in one of those directions circular motion is happening, and in the other there's no movement. And let's start with the vertical plane. So I'm going to resolve vertically because P is not moving up or down or being accelerated up or down vertically. It's continuing to stay in a horizontal circle. So the forces acting at P must balance out, ups equal downs. Well, what have we got? We've drawn them all in, let's write them down. We have 2T cos 30 for one of the tensions, and we have a component T cos 60 from the other tension, and that's equal to the weight force downwards, 0.4 G. Well, T is a common factor of everything there. Let's take T out, and we have 2 cos 30 plus cos of 60. And that's equal to 0.4 G. 0.4 G is 0.4 times 9.8, and that's 3.92. And then I did a little bit of substituting over here as well, because cos 30 is root 3 over 2. If I multiply that by 2, I get root 3. I'm writing down exact form rather than decimals, so that I don't introduce any inaccuracy. Cosine of 60 is exactly 1/2. So there we go, I've got a nice exact statement there, which means I can find T. T will be equal to 3.92 divided by root 3 plus 1/2. And I calculated that to be 1.75623, etc. So 1.76 newtons to 3 significant figures. Now the question asked us to find the two tensions acting in the strings. So that particular tension, that's the one that's acting in BP. And in the other string, AP, I have 2 times that. and that tension is 3.51 newtons. I did go back to my original version rather than doubling 1.76, as you can realise. So there we go, I have the tension in the two strings, and that's the first part completed. There were 4 marks for that. First of all, one for correctly resolving vertically, and then a second method mark for getting each part of that expression correct, and then a mark for each of the tensions. Well, I've answered the first part of the question, which was to find the tensions in the strings. The second part asked, what is the angular speed of P? Well, in that case I've got to consider what's happening horizontally. P is carrying out circular motion, and therefore there has to be an acceleration towards the centre. That's r omega squared. So the resultant force towards the centre must be producing that circular motion. So I'm going to use F equals ma towards the centre. Well, let's find all the components acting towards the centre. There's a component of each of the tensions, and that's it. So we have 2t sine 30 plus t sine 60. That must be equal to the mass times the acceleration. The mass is 0.4 and the acceleration is r omega squared. Well, some of these bits and pieces I can deal with a bit more easily. Sine 30 is a half, so 2 times t times sine 30 is 2 times t times a half, which is simply t. Then sine 60 is root 3 over 2, so that's t times root 3 over 2. Now over here I've got 0.4 times the radius, which I happen to find out back over here was 0.5 times sine 30, or 0.25. So that's r, and I'm trying to find omega, so I still have omega squared on the right there. Well, on the left I'll take out t, but I do know t, and I made sure when I calculated this that I used the exact value of t which I'd stored rather than a rounded value. And on the right, 0.4 times a quarter is 0.1. So I've got that times omega squared, so I thought to myself I'll just multiply everything by 10. So omega squared is 10 times t. Now I'll write down 1.76, but as I said, I carefully used the answer which I'd stored rather than the rounded value, and it's that times 1 plus root 3 over 2. Well, working all that out and square rooting it, I ended up with omega equals 5.72. And the units for that are radians per second. That was my answer to 3 significant figures. There we go then. So basically we resolved vertically and set the forces equal. We resolved horizontally and considered the forces towards the centre being equal to mass times the acceleration. And for this second part of the question, there was a mark for using F equals ma towards the centre, and then a second mark for getting the various parts of that expression correct, and the third mark was for the answer. Well, there's one question. Now let's look at another one. Take a moment if you wish to pause the recording and read the question through. And what we have is an object rotating around the surface of a cone. So it's attached at the end here. The string is of length L, and we have a mass m. We don't know the mass, it just is mass m. If it's carrying out circular motion, it must have an acceleration towards the centre, and given we're told the angular speed is omega, then the acceleration towards the centre will be r omega squared. and of course there's a weight force and a reaction force. So, what does the question ask us to do? It specifically tells us to resolve horizontally and to resolve vertically, to find two equations this time, involving t and r, and hence show, and then we have this expression to show. Then in the second part, we're told the length of the string, and asked to calculate the greatest value of omega for which the particle remains in contact with the cone. Because I guess if this blob m is circling fast enough, it might be able to spin a bit faster and move off the surface. So we're trying to find the value of omega just before it leaves contact with the surface. Okay, once again, let's get everything onto the diagram. Well, we don't know what the mass is, but we do know that there's going to be a weight force of mg newtons. And then, because it's carrying out circular motion, as we said, there has to be an acceleration towards the centre, which is equal to r omega squared. Be useful to know the radius of the circle, actually. And we know the length here, L, this is a right angled triangle with 45 degrees there, so the radius of the circle will be L times sine of 45. Might just be useful to mention at this point that sine of 45 is the same as cosine of 45, and in exact form it's 1 over root 2, or you may prefer to use root 2 over 2, which will get you the same answers. Well, so if r is L times sine of 45, it's equal to L over root 2. There's the radius of the circle. Right, so what forces have we got acting other than the weight force? There's a reaction force perpendicular to the surface of the cone on which this action is taking place, and that is R. And then of course we have the tension in this string here. So that tension is T, and I'm going to need to split both those forces into components horizontal and vertical. So if this angle is 45 degrees, then so is that angle. And if there's a 90-degree angle between T and R, then this angle is also 45 degrees, which means everything's got 45 in it. Let's resolve R into two components. The one next to the angle will be R cos 45. The one opposite, R sine 45. And then to the left, there's a component of the tension, there's another component of the tension, and this will be T cos 45, and upwards T sine 45, although of course those will actually be the same because it's an isosceles triangle. Well, what I'm going to do then is what I did before. Let's consider what's happening vertically and what's happening horizontally and see what that where that gets us. So vertically then, we have the component of the tension upwards, the component of the reaction force upwards, and the weight downwards. We've got T sine 45 plus R sine 45, and that's equal to mg. Well, of course that means I've got both T and R times sine of 45 equal to mg. Well, sine 45 is 1 over root 2, so T plus R times 1 over root 2 is mg, and therefore at its simplest I've got T plus R equals root 2 mg. Well, there's an equation with T and R, and I guess what's going to happen is I'll get a second equation with T and R in from resolving and considering forces horizontally. Well, because the circle is happening in the horizontal plane, I'm going to consider f equals ma towards the centre. And what forces have I got acting towards the centre? Well, t cos 45 is acting towards the centre, r cos 45 is acting the other way. So I have t cos 45 degrees minus r cos 45 degrees. And that's equal to m times the acceleration. Well, the mass is m, I don't know any more than that, and the acceleration is r omega squared. Well, once again, I can take cos 45 out as a factor, which will give me t minus r times cos of 45. But I do know the radius of the circle, so I've got m times the radius, which I've written up here. It's L over root 2. And it's that times omega squared. And on the left there's a root 2 as well, of course, because cos of 45 is 1 over root 2. So I have t minus r times 1 over root 2 equals m L omega squared all over root 2. So if I multiply both sides by root 2, I'll end up with t minus r equals m L omega squared. And there's my second equation. So it looks like I should be doing simultaneous equations to sort this out. Let's write down the two equations. So I had the following: t plus r equals root 2 mg, and that was my equation 1. And then t minus r equals m L omega squared, and that was my equation 2. And let's just refresh our memory about what the question asked, because we're asked to find an expression for t. Well, I think then if I were to add these two equations together, 1 plus 2 will eliminate r. T plus t is 2t, r minus r is 0, and that leaves me with root 2 mg plus m L omega squared. Well, on the right there's a common factor of m, so let's take that out. I've got m times root 2g plus L omega squared. And that's what 2t is equal to, so if I half both sides, I end up with this expression here, which conveniently is exactly what we were trying to find. And the mark system for that is there's 1 mark for eliminating and 1 mark for solving to get this expression, or rearranging to get this expression for t. Well, that's found the expression they asked for t, and now let's proceed to part 2 of the question, which said, when the string length is 0.8, calculate the greatest value of omega for which the particle remains in contact with the cone. So fact number 1, L is 0.8, but the other thing to consider is the critical value for the object being in contact with the cone. Well, whilst it's in contact, it has a reaction force. So when the reaction force is reduced to 0, that's the moment when it's going to leave contact. And it needs to be just when that happens for the first time, because obviously once it's spinning around in the air, r will continue to be 0. So this is the critical value when r is 0. R is 0. Well, I've got an equation above for t, but I think if I did the opposite and did equation 1 take away equation 2, I'd eliminate t and be left with r. So let's do that. T take t is nothing, and r take minus r is 2r. And that's equal to root 2 mg minus ml omega squared. And I'll just pop in at that stage the 0.8 omega squared. And significantly, we're going to use the fact that r is 0, so this left hand side is going to be 0 anyway. So I've got 0 equals root 2 mg minus 0.8 m omega squared, but if it's all equal to 0, I could divide through by m, and of course we find the mass doesn't affect the outcome. I'll add 0.8 omega squared to both sides, and that's equal to root tg, which means omega squared is root 2g divided by 0.8. Well, those of course are all numbers, so I can work out the right hand side and square root it, and that gave me an answer of 4.16 radians per second. So if it goes any faster than that, it's going to leave contact with the surface of the cone. Now then, just want to confirm how this question was marked. So I'm going to go back to the beginning. There was a mark for resolving vertically and for getting the components in that right, so the intention and then the execution, a mark for the method and for the answer. And the same horizontally for resolving and getting the components correctly. So that's the 4 marks there. The next couple of marks were for adding the 2 equations to eliminate r and rearranging to find the version that we were given. Don't forget, because the answer was given, there's no marks for actually writing that bottom line. You have to show you've arrived at it. Then the 4 marks for part 2 were given as follows. 1 for using the fact that r equals 0. Then, by subtracting the equations instead and ending up with an expression like this one here, or that one below, there's another mark. Solving that to find omega was a method mark, and finally getting a mark for the value of omega to answer the question. Well, I hope that was useful in your revision for horizontal circular motion. Don't forget to look at the other recordings on the FMSP website for OCR M2.